Yeah, so today we're going to be going through the transition dipole moment integrals. We've done a few of those as they were, showing up in the problems, but today that's what our main focus is to looking at the symmetries of these for the intensity calculation. So we're down here at the bottom of our scheme. We started with the Lewis dot structure, came up with the Vesper shapes, that gave us a geometry. We ran that through the character table, not the character table, the flow chart, and came up with the point groups. Hopefully you're getting to the point where you don't need the flow chart as much, where you have sort of classic examples of molecules that you can compare other molecules to. So what would be an example of a C2V molecule?
Water.
Yeah, it should be just like that, water. And so then when you see formaldehyde, you got a carbon double bonded to an oxygen and two hydrogens. You look at that molecule and you say the left and right are the same, the front and back, it's planar, it looks just like water. Even though it's not chemically anything to do with water, symmetry wise, it has the same symmetry as well. Ammonia. What is ammonia? C3V. So then when you have chloroform, you have a carbon, a hydrogen, and three chlorines. C3V, yeah. So you should be able to sort of get away from the flow chart with classic examples of molecules in your head. Okay? Octahedral, SF6. So something with six identical things around it, okay, would be an octahedral. So SF6 would be a classic octahedral. Any of the water complexes that are hexavalent or whatever, you have water with six ammonias around it, ignoring the little positions of the three hydrogens, you've got six ammonia molecules around a cation in water. That would be an octahedral complex. Tetrahedron.
If off the top of my head, it's most copper one complexes.
Yeah, but make it easy. Methane. Yeah, so CH4, methane. Yeah, so tetrahedral. Yeah, exactly.
Sorry.
Cobalt. Yeah, cobalt makes some tetrahedral complexes. So anyway, that's the point groups. Then we go through the character tables, and the character tables allow us to do the symmetries of all of these things. And we've spent a week or more going through the symmetries of vibrations, the symmetries of the molecular orbital. So that's where we've been for a week, is using the character table to come up with the labels of these energy levels. The energy levels have been vibrational energy levels or been molecular orbital electronic energy levels, but we've been labeling them with the Millikan notation. And so down here now, we are to the point where we're going to use the direct product tables to determine the selection rules for spectroscopy. So we now know the wave function of the upper state, the wave function of the lower state, and light. And we can see if the intensity is going to be zero. So we're going to integrate those, but we're not going to integrate the functions because they're too complex. I would not have a chance of doing it. Okay, but I can look at the symmetries and determine if they're going to be zero or non-zero. So the symmetry of the total wave function is all of the individual wave functions times each other. So it's the product of all of those wave functions. So if you look at that, you can see that we might have, let's see, let's just pick something like say water. Remember water was C2V, and we have A1, A2, B1, and B2. And so the total symmetry of this wave function, you might have an electronic wave function that's B2. You might be in the ground state vibrational level, which is A1. You might be rotating around the x-axis and be in an excited state, maybe the first excited state on the rotation, and be in a B1 state. And then there's a nuclear wave function too. Have no idea. I'm going to pick A1. Okay. We haven't talked about nuclear wave functions. But what do you think the total wave function symmetry is? Well, it's the product of all of these. And so we have these waves that interact with each other and they multiply. And so we get products of symmetries and we can come up with the symmetry of the total wave function. Okay. So with integrals, the intensity from n to n prime of a transition is going to be the square of the integral of the transition dipole moment. Okay, so this transition dipole moment integral is right here. Now Dirac shortened that integral notation to these angle brackets. So this is the same thing. And we can use symmetry to know if this is equal to 0. So if the result of this direct product, so the integrand, this thing in the middle, so the thing that's being integrated is called the integrand. If that integrand is not even, then the integral will be 0. So what do we mean even? Even means top row of the character table. So it will be forbidden by symmetry. If that integrand is not the top row, then this integral will be 0, and we would call this a forbidden transition. So I've just emphasized this again. If the direct product result does not contain the totally symmetric irreducible representation, which is the top row of the character table, notice I have to say it that way, because in some character tables, top row is AG. C2V character table, it's A1. Some others, it's just A. So I can't give you an A thing. I have to say top row. So whatever point group I'm in, I look at that character table. Top row is the only one that's going to be non-zero. If I have an integrand that's top row symmetry, then it can contain it. It can be a sum of a bunch of symmetries, but if one of those symmetries in that sum is top row, we're good. It'll be non-zero. Okay. If it doesn't contain any top row elements, then it's forbidden by symmetry. So let's do this in many examples. So we use the Vesper theory to create the geometry. Geometry gets a point group. We find the Millikan symmetry of those wave functions. We could use the projection operator and reducible representations, or we could do it by inspection. The last couple of times we've been doing this by inspection. And then we need to pick the symmetry of light. So how is light coming in here? For direct absorption or emission, it's just the polarization of the electric field. So is it coming in polarized along the x-axis, the y-axis, or the z-axis? For scattering, it's some second order combination. So it could be x squared, y squared, z squared, x, y, x, v, and y, z. And then we use the direct product table to determine the symmetry of the integrand inside the integral. So let's do it. So let's go back to the particle in a box. We have our 4 wave functions here. We only have E and I symmetry elements. So that's our character table. So Ci is our character table. Top row is Ag. Okay. And so we have, for light, we're going to pick the x, because we only have the x-axis, because it's a one-dimensional system. So we're going to put x in the middle. And so we're looking to see if that's an allowed transition, the 1 to 2 transition. So we can put the symmetries in there. So the symmetry of level 1 is Ag, the symmetry of level 2 is Au, and light is Au. So the x-axis, light coming in polarized along the x-axis is going to have Au symmetry. So we can use the direct product table for these steps. Now I realize this is such a simple example. You may say, well, this is obvious. Why is he going through all the steps? But these are all the steps that you do on the more complicated examples. So we do them right to left. That's just the convention. For just like matrix multiplication, you would do the same thing. So Au times Ag is right here. Au times Ag is Au. So we bring that Au down. And then we have Au times Au. So then that's this one right here. X equals Ag. And that's the top row of our character table. So this integral is not 0. Yeah, so I'm just going to say top row here. There. So the 1 to 2 transition is allowed. What about the 1 to 3 transition? Same symmetries. So we could just look at this and say, yeah, this one right here, that's a terrible arrow, but you get my idea. Okay, also allowed. Because of the same symmetry. Okay. What about AU to AG? What about this one? If you'll notice here, if we swapped this U and this G, that's all we would be doing. And if as long as we have an even number of AUs, they're going to cancel each other. If we have an odd number of AUs, then we got a problem. So if we're trying to go from, let's see, do I have that as the next one? Yeah. Can we generalize? Yeah. So these general rules are, as long as we have an even number of AUs right here, and I say good and bad. Good is if we want a spectral transition, and bad is if we don't. Okay, so and because you remember these U's and G's, you think of them when they're multiplied by each other, kind of like minus ones and plus ones. So if you've got a string of ones multiplied by each other, if you have an even number of minus ones, they're going to cancel. If you have an odd number of minus ones, you're going to end up with a minus one in the end. So that's how we know the U's represent minus one, G's represent plus ones. And so we would go through this as if we have an odd number of U's, the end result's going to be AU. What about scattering? Okay, let's use the x squared operator. So now this is the Raman setup. So is this allowed in Raman? So x squared up here is AG. So x squared is AG. It looks like we're going to have an odd number of U's. So this is going to be forbidden. So let's just quickly go through it. And yeah, so see the AG's don't do anything. That's AG. And then the AG times AU is AU. So this is not allowed. So light scattering cannot cause the 1 to 2 transition. Okay. What scattering is allowed? We need an even number of AUs or no AUs at all. And so I could cause a jump from G to G. I could cause a jump from U to U, you know. So I end up with the delta N equals 0, which would be that one. That's G to G. Or I could do 2 and 4. It could go from Raman scattering to level 3, and then Raman scattering from 1 to 4, etc. Or from 1 to 5. What about rotational levels? So this is everything with our particle in a box. So that's a bit of a review. Now let's get into the 3 spectroscopic techniques we've talked about so far. We talked about rotational motion. And so here, put a star by this line, okay? For rotational energy levels, the even quantum numbers are even symmetry. They're top row symmetry. So we have in their energy level diagram, notice when J equals 0, I have A1. When J equals 2, I have A1. When J equals 4, I have A1. Okay. But when the quantum number is odd, it's the symmetry of the motion. So it doesn't necessarily have to be B1. It's the symmetry of the motion. So the odd quantum numbers here means they match the symmetry of the motion. So wherever Rx, Ry, Rz. So if it's Rx, then it would be whatever row that Rx is on would be right here. If it's Ry, then whatever symmetry Ry would be labeled right here. Okay. And then it just alternates top row, Ry, top row, Ry, top row, Ry, all the way up. Okay. So let's look at the selection rules for this then. So can this molecule be excited by direct absorption of light? Psi evens would be A1, psi odds would be B1 for this particular rotation. See, the rotation around the y-axis is B1. And Rx is B2 and RZ is A2. So here's for so this is the J equals 0, this is the J equals 1, and this is light in the middle. Is everybody cool with that? See, the J equals 0 is A1. Rotation, let's see, Z polarized light down here. Here's Z polarized light, that's A1. So that's where we get A1. Yes. J is our quantum number for rotation. Yeah. Let me go back a slide. So here's our energy equation for rotation, for rotational motion. And so our J values are the quantum numbers. Yeah, that's a good question actually, because I changed into a new spectroscopy, a new energy equation, a new quantized system. And this is the rotational energy levels plotted here. So this E of J is plotted right here. So this is the E0, E1, E2, E3. And these are the symmetries of those. Yeah. So we set up our transition dipole moment integral. And notice when we do that, Z polarized light, the A1s carry down, and then we have B1 times A1, we end up with B1 in the end. And so this is going to equal 0. I'm just going to put it on there, Z equals 0, because it's not the top row. Let's do it with X polarized light. Okay. Yeah, X polarized light is B1. And rotation around Y is also B1. And so notice that those are a match. So B1 times A1 is B1, and then B1 times B1 is A1. So this is not equal to 0, and this is allowed. So we can pretty much say if I've got rotation around Y here, it's going to be X polarized light that causes it to absorb. And if I have rotation around X, it's going to be Y polarized light that allows it to absorb. Because if I'm going from an A1 level to a B1 level, the A1 isn't going to change anything. I need something to interact with this B1 level. In other words, I need another B1 to make this pairing, into an A1. So this is very useful in the character table. I can just say that rotation around Y can be excited by X polarized light, and rotation around X can be excited by Y polarized light. What about Z? I don't have anything that can excite rotation around Z. So there's nothing that can cause water to spin this way. Light can't come in and spin water that way. It also makes sense, right? Because if I'm just rotating the molecule, there's no dipole that water can interact with. So there's no light, no polarized light that can come in and cause water to spin this way, because there's no dipole that way. But there's a dipole this way, and I can cause it to spin this way, or I can cause it to spin that way. But I can't cause it to spin around the z-axis. So that's rotational motion. And we haven't even gotten into rotational wave functions or anything. Yeah. So Ry is allowed by X-pole light, and Rx is allowed by Y-pole light. So that's basically what I was just saying by hint. Okay, let's do vibrational levels now. Here's our new energy equation. So our quantum number is V. Here's our quantum number. This is our vibrational frequency. This also alternates. The symmetries alternate. So the even quantum numbers are top row. So we see those over there. I'm going to make them blink for you. So you see those are the top row, all the even ones. And then the odd ones are whatever that vibrational motion is. If it's a B1 or a B2 or whatever. So the odd levels are the symmetry of the motion. So if we're going to do the asymmetric stretch, this one here in water, so the hydrogens and the oxygens are stretching asymmetrically, then that's going to be a B2 motion. That's motion in the y direction. Okay. So let's do the selection rules. Can this vibrational mode be excited by light? So our even quantum number is, our even wave functions are A1, our odd ones are B2, and here's the three different polarizabilities of light, or polarizations of light. So if we use Z, we get an A1, and once again, that doesn't cancel with B2 to give A1. So this one's going to be equal to 0. So Z polarized light cannot do it. What about Y polarized light? So once again, if we're starting in a symmetric state, we need something to cancel the oddness of B2. We don't have any U's, but it's like we need two U's, right? And so we need a particular type of U. We need a B2. We need an odd wave function that's going to cancel the odd wave function from vibration. So light and vibration have to match. So we end up with B2 from the first pairing, and then B2 times B2 is A1. So this is not equal to 0, and that's allowed. So Z polarization will be allowed by Z polarized light. It's kind of messy. So we just have, if I have the symmetric stretch, like this one, the dipole's oscillating up and down. That's a Z dipole moment. So that motion has Z symmetry. And light coming in with the Z polarized light can interact with that. And so that would cause that transition to occur. So for the infrared, if I have a motion that's labeled with Z symmetry, then Z polarized light can cause it to occur. Same with X and same with Y. Let me pause here before we get into molecular orbitals, just to make sure I clarify anything that you want straightened out. What do you think? You following along? Okay. Yes. Rotation. Yeah. Yes. Yeah. So in this one, we're just looking at the X. And so if the motion has X symmetry, then X light will interact with it. Same with Y. Whereas previous, I was looking at rotation. So they were kind of swapped. This was rotation around Y, excited by X light, and this was rotation around X, so excited by Y. I think that's right. Yeah, that's right. So here's the electron cloud, and it's also oscillating. So the electronic energy levels, they do not have any alternating trends like we do in rotation and vibration. Okay. So here we have the HOMO to LUMO transition in ammonia using Z or XY light, and we can calculate those. So for Z polarized light, it's A1. So everything's A1. We know that's going to be allowed. If you have A1, A1, and A1, you just, yeah, it's even all the way across. Okay. So that one's allowed by symmetry. What about this one? Well, we have E1 times A1 gives E. I keep saying E1, it's just E. And then A1 times E is E. So XY polarized light cannot cause this transition to occur. And it does kind of make sense if you look at the picture. So looking at this picture, I've got oscillation on the Z axis. And up there, it's kind of like oscillation going out. The middle is shrinking while the outside's expanding, and then the outside's shrinking while the middle is expanding. And there's green on the bottom, so it also kind of weakly oscillates in the Z direction. It's just below the nitrogen. And so Z polarized light would interact with those orbitals. You know, if you put an electric field on there with light, then it would interact. If I come in it with X polarized light, it's not gonna cause those waves to interact. So the result is that this is allowed for Z polarized light only. It's not as simple as just counting up how many ways it can absorb, but that does affect intensity to some degree. Like something that's allowed for X, Y, and Z should probably be more intense in terms of an absorption than something that just has only one way for it to absorb light. Just statistically, right? If a molecule is rotating in space and light hits it, if it doesn't matter what the orientation of the molecule is, then it should be a stronger absorber than if it has to be lined up in a particular way. So the MO selection rules are not easy like the vibration and rotation ones. See, because we don't know what those MO symmetries are by definition. See, rotation, we know that, you know, if we're starting for vibration from the fundamental, the 0 to 1 transition, we know this one is always top row. And for rotation, if we're doing the 0 to 1 transition, we know that the 0 is always here in terms of top row. But for molecular orbital theory, we can't just automatically assume this one is A1 top row. We have to look at it and walk through the character table and make sure we know both of those. We have to assign both of them. So that's why we can't just look at the character table and say, oh, this is a homo to LUMO transition, so we know that it's X or Y. We can't do that. We've got to actually look at this orbital shape, walk it through the character table, and see what symmetry it is. And so we still need to do the light also X, Y, or Z. We would use the character table to determine those. We don't know any of the three parts. For these two, we always have at least one of those parts is A1. That is, if we're doing like a delta J, a delta V, or a delta N of just plus or minus 1. We might have, like if we were doing, say, a Raman experiment, so that would be delta J equals plus 2. You know, then we would know this is A1. So it's going from A1 to A1. So what would we need here to make that the case? So we have A1 on both ends. What do we have to have here, symmetry-wise? If I want this to be non-zero, I have to have an A1 in the middle. And so then I would go to my character table and see what's on the top row in terms of interactions for this molecule. It might be Z polarized light. It might be, this is Raman, so it might be Z squared. It might be X squared plus Y squared. It might be something, but if there's nothing on that top row that is second order in Raman, then I can't do Raman on this transition. It won't be allowed. Okay, so let's practice a little bit with these. So here's the normal modes for acetonitrile. And these are vibrational frequencies, so vibrations. Yeah, vibrational modes, you see these. So all of these symmetries here are A1 for 1 through 4. And so we know that this is A1 for all of them, and this is also A1 for these top 4. Okay, so what kind of light do we need? So we have A1 on both ends. What do we need in the middle? We need an A1, right? So that's going to be Z polarized light for direct absorption. So this would be allowed, all of these would be allowed in the infrared. I'm gonna put Z in parentheses. Is that cool for everybody? So allowed in the infrared with Z polarized light. What about the Raman experiment? So that's the same for all four of these. Is there something on the top row that is a Raman experiment? Yeah, these right here. So this is also allowed in the Raman. Z squared, etc. Okay. So at least the first four vibrational modes in this molecule are allowed both in the IR and in the Raman. Okay. What about the E one? So now we've got a different situation for these right here. It's E and A1, and we need something in the middle. Yeah, so we would need E in the middle. And so that could be XY, X or Y, polarized light, or X squared minus Y squared, X times Y. There's lots of ways the Raman would work. Or XZ or YZ. All of those would give us an E in the middle. So let's do that one though. Let's take this and we'll say E times A1 is E. And then E times E, if we go find the direct product table for C3V, we see it's A1 plus A2 plus E. I don't expect you to have that memorized yet, but it'd be a good idea if you did. E times E is A1 plus A2 plus E. You'll see that in the direct product tables. But here's the thing, it contains A1. Not equal to 0 alone. So these are also allowed in the IR and Raman. So when you compare the two spectra for acetonitrile, you'll see the same peaks, the same frequencies. You'll see different intensities maybe, but they'll be the same vibrational frequencies for each of these. See how useful the character table is? See how disastrous it is if you get the wrong point group. Yeah, right. So okay, let's look at ethene. So we have all of these MOs, and notice how there's, it is coincidental that the very lowest one is AG, but it doesn't have to be, and then we have B3U and B2U and AG, B1G, B1U. The U's and the G's are all mixed up, they don't alternate. It's just a mess. Okay, but that's what the electron cloud is doing. It's not equally spaced energy levels like the vibrations or anything like that. Yes.
These last couple of slides, at least when I downloaded the lecture, weren't in there. Would you be able to
This two?
get that one and the next one?
This one here?
No,
This one?
that one and then
this one.
this
Okay.
one, yeah.
Okay. Yeah. I can.
Mine ended with the note about molecular orbital energy levels.
Okay. Okay. Yeah. Are you able to still take notes?
Yeah, I can
okay.
try to take notes. I just can't.
Yeah. Yeah, that's right. Yeah. What we can do is let's just try the HOMO to LUMO transition. We may have already tried this. Did we do this one the other day? I don't think so, because we just barely got through the ethene one. This is a quick way to determine if something is, is going to be colored or not. Because you look in the visible region, this is the length of the arrow for 400 nanometer light. And it's not enough to hit that level. So right there, that tells me this is a transparent gas. Like if I had ethene in a container, I wouldn't be able to see it. Like if I had NO2, I could see a brown gas in there, so it's visible. You know, you could see a peak in the visible region from NO2. But for ethene, it's a colorless gas. Okay, but still, let's prove. Let's see what this homo-lumo gap, this homo-lumo transition would, if it's allowed. So the highest occupied molecular orbital. I know it's really tiny type. You have to trust me. It's B1U. Okay, so that's that one. And then the lowest unoccupied molecular orbital is B2G. Okay. Now we got to figure out if there's any light that would essentially convert B2, or let's do it this way. What if there any light that can convert B1 into B2? So here's a B1, and I want to end up at a B2, so that when I take B2 times B2, I get A1. Okay, so I'm kind of jumping ahead. So I would need something with B3. So I've got right here B3U is X polarized light. So X polarized light is B3U. That's good. And I've got an even number of U's. So it's looking really good. Let's show it. Okay. So I've got B3U times B1U gives B2G. See that? I went B3 times B1 gives B2. And then the U times U gives G. And then now I have B2G times B2G. So B2 times B2 gives A. And G times G gives G. And that's my top row. Not equal to 0. Allowed with X polarized light. Yay. So the homo-lumo transition is allowed. That's great. Now it isn't in the visible region according to this calculation. Now in order to keep things simple, I did this with the minimal basis set, STO3G, not 6-31G star and so on. So I wanted it to be very obvious which atomic orbitals went into the molecular orbitals. So this gap is going to be probably much larger with such a weak basis set. So I didn't give my electrons enough freedom to really get accurate energies, but that's really not that important. But so that's how you go from determine if this transition is allowed. So yes, right? Which do we want to do another one? Which other one do you want to do? I don't see any B1Us up here. I see an AG. Let's start on our B1U again, our highest occupied molecular orbital. Okay. And let's say we're going to go to a B3U, this one here, B3U. Okay. You're shaking your head. Why are you so fast? Why not? Yes. Nothing multiplied by B1, they get B3. Well, here's a B3. So if it was B2 multiplied by B1, I would get a B3. Okay, so a B2 would work here. So that would work, but there's another problem. I've already got two U's. Yeah, B2G would work. Okay. What is B2G? Well, it's XZ. It would be allowed in Raman, but not in IR. I mean, not in direct absorption, visible, or wherever the difference is. So direct absorption would not work because all of the just single like polarized lights, X, Y, and Z, they're all U. And if I try to do B2U, then I'm going to end up with AU in the end. Does that make sense? I have an odd number of U's, and so it's not going to be allowed. But if I had a B2G, then this would give B3U, and B3U would give AG. Yeah. Which is not equal to 0. So allowed for XZ Raman scattered. What do y'all think of that? You had your hand up.
Yeah, in this case, so we have to do it still.
Start again. I missed a syllable. That's okay. Start again. Yes, correct. So it's because people are lazy. So, you've got A1 times B1 is B1. Well, this is A, and this is A, and this is B1. So this is also B1. So it's symmetric around the diagonal. So this is B2 and this is B3. No, is that right? Yeah, B2. This is B3. This is B3. This is the opposite of B2. So B2, and this is B1. Yeah. So it's just, again, they're saving ink. That's right. Yeah. So that's why I say humans are lazy. Dirac is a human. Aristotelian logic here.
Also, all
There you go. Yes, I like it. Yeah. So, but I kind of jumped ahead instead of going through the tedious saying of trying X and saying forbidden, and then trying Y, it's forbidden, and then trying Z, it's forbidden. I kind of jumped ahead and said I've got a B1 and I've got a B3. Is there anything that can convert that B1 into a B3 using the direct product table? If there wasn't anything at all in the whole table, then it would also be forbidden. There'd be nothing. But we saw that a B2 in the middle would cause us to get top row. And then we just look to see, is there any kind of light that would allow that transition? And yes, a Raman experiment would allow that transition. What if we came up with something that was like AU would allow it? So we could get the transition dipole moment integral to work if light was AU, but when we look at the AU row, it's not Raman, it's not direct absorption, so none of the experiments that we know of would cause that transition to occur. So we would just say forbidden in the infrared, or I keep saying infrared, forbidden for direct absorption and forbidden for Raman. There aren't any other experiments that we're analyzing in this course. I don't know what else there is. There's Raman scattering, Rayleigh scattering, direct absorption, and emission. And that's, what else is there? If you think of something new, tell me. Right? But there's spontaneous emission, which is emission. There's stimulated emission, which is emission. There's absorption. there's Rayleigh scattering, there's Raman scattering, Stokes and anti-Stokes. I don't know what else. Yeah, I mean, there's two photon ionization maybe, but that's still a two photon process. I mean, there are some other spectroscopic techniques, but these are the ones. This is enough, don't you think? Absorption, scattering. Okay.